Dear students, today we will learn concepts of field, scalar fields, vector fields and their calculus. That means integration and differentiation related to the concepts of field. This is purely mathematics. Today we are learning or in another 2 or 3 hour sessions. But it is very important to understand the concepts and the nature of electrical interaction, field, all those things in electrostatics and electricity and magnetism. Therefore, uh, learning about electricity and magnetism involves learning of some new mathematics also, which you haven't learned till today, even in mathematics. Uh, uh, in this session today's session, I am going to cover all these concepts. Uh, Concept of field, its definition. It's not very precise or rigorous definition I am going to give, but an intuitive understanding about the field and its definition. Then we will study scalar field, vector field, and few examples related to both of them. Then we will start learning differentiation of this field. Especially in today's session, we are going to learn about differentiation of scalar field. And in many ways, we can define the differentiation of a field, but we have found only mainly three first order differentiation, uh, for one for scalar field and two for vector fields. Two for vector fields. Uh, the differentiation of scalar field is called gradient. It gives you a vector field. Okay. Uh, we are going to define in Cartesian coordinates only, which is easier to understand and compute also. Then we will introduce a symbolic operator, vector operator del, and we will denote it by a this symbol which I have shown on the this one. Let me highlight first, select pen. This is the symbol for del operator. Later in this session we will consider the geometrical meaning of the gradient. And after at last I am going to explain you where these gradient concepts are coming in physics. Okay, with this we will end today's session. Let us first start with the definition of the field. Field is a region of space in which a physical quantity is associated at every point of space. Okay, if you consider a region, and that every point of that region you have to associate certain physical quantity. Let me say temperature. Okay, this is a hot iron bar which is very hot, and whenever it is hot, surrounding air will get hotter. Okay, therefore at every point we can define temperature around that hot source. We will define temperature. Here it is, let me say 230 degrees Celsius. Here if you come, it is quite near to this source, therefore it will be hotter, say 323 degrees Celsius. Here if you go, it may be still closer, it is, therefore it will be uh, hotter, more, say 373 degrees Celsius. Okay, means at every point in this region, everywhere you have to associate certain physical quantity. Here it is temperature. It's a smoothly varying field. Means I can define a very nice continuous function which gives the value of this temperature at every point. Therefore, in space, it is easier if we introduce coordinate system XYZ to recognize a point. By introducing such coordinate system, I can recognize a point as X, Y, Z. Therefore, what is this field? Now, temperature field is a function of X, Y, and Z. This is a smoothly varying function, means it has certain mathematical properties which allows us to differentiate and integrate all those things. It's a continuous function. Now you recognize T is a different dependent variable. T, temperature, here it is a dependent variable. Dent variables. I will change the color so that you may recognize it easily. Then these X, Y, Z are independent variables. X, Y, Z are independent variables. Therefore, now this has become a function of many variables. Function of many variables. Therefore, whenever differentiation is involved, you should consider partial derivatives such as dou by dou x of t, dou by dou y of t, like this. You have to consider partial derivatives. Therefore, you must be thorough in computing partial derivatives. Not only ordinary derivatives, partial derivatives. Now some physical examples as I have explained here. Once again I will go to some other color. As I have explained here, temperature distribution around a hot iron bar is a physical example for field. It's a scalar field because temperature is a scalar quantity, right? Therefore, at every point we are associating a scalar. It's a example for scalar field, and scalar field means a scalar quantity smoothly assigned. Smoothly means in a mathematical fashion it is continuous, assigned to each point of a certain region of space is called scalar field. Temperature field is a scalar field. Similarly, in electrostatics, electric potential, not electric vector, electric potential around a charge, your voltage or potential, that is a scalar field. Similarly, if you assign a vector quantity instead of a scalar quantity at every point of region of space, then that is called vector field. That is called vector field. How to visualize vector field? It's a visualization technique only, not an exact picture of field. At some representative points, you can draw a vector which shows the field direction and its magnitude. Okay, here it has more magnitude and direction is in this point. Here if you come, it is very uh, magnitude is less and direction is almost as shown in the figure. But this is not an accurate picture, because at every point you should define such vectors, not only at this point or at this point, like that. And physical examples for vector field is magnetic field around a magnet and electric field around a charge. Okay, they are vector quantities. Therefore, at every point around the charge or magnet they are defined. Therefore, they are called vector fields. They are the examples of vector field. And this diagram I have taken it from Wikipedia Commons. Now let us learn the definition now and gradient, and let us compute gradient of some scalar fields. They are prototype examples. Okay. Uh, First, how do I represent a field which is a scalar quantity? Scalar quantity means one number is enough at every point. One number is enough at every point. ಒಂದು ಬಿಂದುವಿನಲ್ಲಿ ಅಥವಾ ಒಂದು ಪಾಯಿಂಟ್ ನಲ್ಲಿ ಒಂದು ನಂಬರ್ ಹೇಳಿದ್ರೆ ಸಾಕು, ಆ ರೀತಿ ಎಲ್ಲಾ ಪಾಯಿಂಟ್ಗಳಲ್ಲೂ ಹೇಳಬೇಕು ಆ ಸ್ಪೇಸ್ ರೀಜನ್ ಅಲ್ಲಿ. then it is a scalar field. Mathematically I can represent a scalar field by some symbol, say phi, which is defined over this spatial region. At every point this is defined. Then if it is a three-dimensional spatial region, I have to consider three independent Cartesian coordinates x, y, z. Therefore, any scalar field can be written as a function of spatial point coordinates. Now I am going to define gradient. Gradient. Okay, I have to define it for some reasons only in Cartesian coordinates. It can be defined in other kind of coordinates, say polar or spherical polar coordinates or cylindrical coordinates or any other coordinate system. But quite it is involved. Now let us learn simplest thing at the beginning, Cartesian coordinate system. That means your favorite XYZ coordinates. In this one, gradient of pi, okay, we will denote like this, gradient of pi. And remember, pi is a scalar field and we define it by taking derivative dou pi by dou x into unit vector along the x-axis, that is I cap, dou pi by dou y into unit vector along y-axis j cap, dou pi by dou z along k cap. Okay, since unit vectors I, j, k have come along with these as coefficients, okay, therefore gradient of pi is a vector field. You remember this uh, definition and practice it with certain number of examples. We will, after that we will consider. You remember gradient of pi can be denoted like this, grad of pi, and defined using the partial derivatives. First you have to differentiate pi with respect to x, then multiply by unit vector I along the x-axis. Similarly, you have to differentiate with respect to y, multiply by j unit vector, dou pi by dou z, multiply by k unit vector. Okay. Later we will have another symbol for this one. After introducing del operator, I will define that one. Now let us practice with examples. A scalar field is given by, say, pi. Pi is equal to 3x square y plus z cube z cube. Now I have to find gradient. Gradient of pi. By definition, grad pi is equal to dou pi by dou x into I, dou pi by dou y j plus dou pi by dou z k. Differentiation of 3x square y with respect to x is given by 3 partially, therefore y will remain same, 3y. X square differentiation will give you 2x whole thing into I, and differentiation of this pi with respect to y will give me 3x square, differentiation of y with respect to y, that is 1, therefore j, then differentiation of pi with respect to z will give me 3z square k. Okay, 6xy I, 3x square j plus 3z square k. Now you see this is also a function of x, y and z. Okay, therefore again gradient is a field, and since I and j k have come, it is a vector field. Vector field. Therefore gradient has to operates on scalar field field and you will get a vector field. One more problem to consolidate the concept of gradient. Let us have this one. Temperature is given by 3x square z yz minus x minus x. Some hypothetical temperature distribution. Whether it is physically possible, we will not worry. Temperature field is like this. Again, let me use the definition to find the gradient of T. Grad T is given by dou x of this T function into unit vector I, dou y of T to j cap dou T by dou z of k cap. And I think you may be fond of computing partial derivatives. Let us practice once again. Dou T by dou x is given by 3z into 2x, and here is also one x is there, minus x, therefore from that minus 1 will come into I plus dou T by dou y. Dou T by dou y is given by y comes here only, therefore it's z into j cap plus dou T by dou z. Z comes in first term also, therefore 3x square plus y into k cap. And further simplification, you will have 3 into 2, 6xz minus 1 into I plus zj 3x square plus y k cap. You can write your own scalar field function and find the gradient. Now we will introduce some variation in this problem. For example, calculate the field value and gradient of the function of the field say f is equal to f of x, y, z. This is a scalar field, is equal to x square y plus z at some points. This is the twist at say at point 1, 2, 3. First you take the gradient as earlier we have done, and then you substitute the values of x, y, z to get the gradient at that point. Okay. Answer I will select some other color. Let me say red. First let us calculate the field value at f at 1, 2, 3. F is given by x square y plus z. Therefore, at this point means you have to substitute 1 for x. Therefore, 1 square into 2 plus z is equal to 3. Therefore, it will become 5. What is the value of field at 123? 0.123, that is 5. 5, let me say, units. And now I want to calculate gradient at f at 0.123, and let me denote it in some fashion. Gradient of f at 123. First let me do the gradient as earlier I have done. Dou x by dou f by dou x, I dou f by dou y, j dou f by dou z, k. Okay. I will use this space so that I can comfortably write, or I will use some other color also for the final answer. Dou f by dou x is given by 2xy I. Then dou f by dou y is given by x square, this is plus j plus dou z by, that is 1k, therefore k vector, or final answer is, you substitute 1 for x, because 1 to 3 point means x is equal to 1, therefore 2 into y is equal to value 2, therefore 2 I plus x square is 1, therefore this will become 1j plus k, or totally at last it will become 4i plus j plus k. Okay, you practice in your home also. Next we will go to define a symbolic vector operation called gradient. Okay, that's also del, symbolic operation.